Something no one predicted just happened at the edge of our solar system. On October 29th, 2025, an ancient traveller older than our Sun, older than Earth, older than anything humanity has ever touched, reached its closest approach to our star and did the impossible. It didn't behave like a comet. It didn't follow the rules we've spent centuries refining. Instead, it exploded in brightness at rates that shattered every model astronomers had built. And the most unsettling part, we still don't know why. What you're about to discover isn't just another space story. It's a mystery unfolding in real time, where the answers we're finding are raising questions that challenge everything we thought we understood about visitors from beyond our solar system. Imagine standing at the edge of invisibility. That's where 3i Atlas existed for most of human history. A silent wanderer drifting through the absolute darkness between stars, carrying secrets from stellar systems we'll never reach. For billions of years, this object travelled alone, bombarded by cosmic radiation, shaped by forces we can barely comprehend, moving through space at speeds that would vaporize anything we've ever built. And then, in one brief moment on October 29th, 2025, as it swung past our Sun at its closest approach, a point scientists call Perihelion, something fundamental changed. The comet didn't just brighten gradually like textbooks predict. It erupted. The brightness surge was so aggressive, so violent, that researchers Chi-Cheng Jiang from Lowell Observatory and Carl Battams from the US Naval Research Laboratory had to recalculate their measurements multiple times just to believe what they were seeing. The data showed brightness scaling 7.5 times more intense than any theoretical model predicted. 7.5 times. That's not a minor deviation. That's not an observational error. That's nature telling us we've been missing something crucial about how these ancient objects behave. Think about what that means. We've studied comets for centuries. We've refined mathematical models that predict how ice turns to gas, how brightness increases with solar proximity, how sublimation rates scale with temperature. These models work. They've worked for every comet we've observed within our solar system, but 3i Atlas threw out that entire framework. The rates didn't match. The timing was wrong. And most importantly, the speed of change suggested something was happening inside that nucleus that our current physics couldn't fully explain. This wasn't just surprising, it was fundamentally disorienting for researchers who've spent their careers mastering comet behavior. Because when something this old, this well-travelled, this thoroughly processed by billions of years of cosmic radiation suddenly behaves in ways we can't predict, it forces us to ask uncomfortable questions about what else we might be wrong about. The blue shift told part of the story. When light from 3i Atlas reached our instruments, the spectrum had shifted toward blue wavelengths, a signature of specific molecules being violently expelled. Carbon compounds, particularly C2, and nitrogen-hydrogen molecules, NH2, were flooding into space at rates that made no sense for an object at that distance from the Sun. These are the chemical fingerprints of catastrophic sublimation, of ice transforming directly into gas so rapidly that the process itself becomes unstable. But here's what made astronomers pause. This wasn't just water ice vaporizing. This was a cascade of different materials, each with different sublimation temperatures, each responding to solar heat in complex ways that suggested internal structures we hadn't anticipated. The comet was losing approximately 1.36 times 10 to the 27th power water molecules every single second. Try to visualize that number. You can't. Human brains aren't wired to comprehend scales that massive. It's 1,360 trillion individual water molecules escaping into space every second. For context, that's more water than flows over Niagara Falls in several hours, except this was happening from an object just a few kilometers across, and it was happening continuously, relentlessly, as if something inside had finally broken open after billions of years of containment. But we couldn't watch it happen. Not directly. That's what makes this entire event so frustrating and so fascinating. Right at the moment of perihelion, the most critical observation window in 3i Atlas's entire journey through our solar system, the comet positioned itself directly behind the Sun from Earth's perspective. Astronomers call this solar conjunction, and it's the worst possible geometry for observation. Ground-based telescopes, no matter how powerful, can't see through the Sun. The glare overwhelms everything. The solar corona creates interference patterns that destroy fine detail. So for those critical hours when 3i Atlas was experiencing its most dramatic transformation, When whatever process was driving that explosive brightening was at peak intensity, we were essentially blind. We had to rely entirely on space-based instruments, satellites like Stereo A, the Solar and Heliospheric Observatory, and GOES 19 instruments specifically designed to stare directly at the Sun without being blinded. These are remarkable tools, capable of seeing things no ground telescope could detect. But they were designed primarily for solar physics, for studying the Sun itself and the solar wind, not for detailed compositional analysis of comets. They captured brightness curves. They measured spectral shifts. They documented the explosive outburst. But they couldn't answer the deeper questions about what was actually happening inside that nucleus. The images themselves revealed something peculiar. The nucleus appeared as a faint, elongated glow, not the sharp, well-defined core you'd expect from a typical comet. The coma, that surrounding cloud of gas and dust that gives comets their characteristic fuzzy appearance, extended across roughly 4 arc-minutes of sky. At the distance 3i Atlas was from our instruments, that translates to millions of kilometers of diffuse material. But what wasn't there proved equally striking. There was no visible dust tail. Stop and think about that for a moment. When you picture a comet in your mind, you see a bright head followed by a long streaming tail stretching across the night sky. That tail is dust, solid particles pushed away from the nucleus by solar radiation pressure and solar wind, creating those spectacular visual displays that have terrified and inspired humans throughout history. But 3i Atlas showed primarily gas emission. The tail structure, when it appeared at all, consisted of ionized gas molecules rather than dust particles. This suggests either unusually ichoric composition with very little solid material to create dust, or it suggests internal structure fundamentally different from what we've come to expect. Either way, it's anomalous. It's a piece of the puzzle that doesn't quite fit the standard picture of what an interstellar comet should look like. The trajectory data added another layer of mystery. This object is moving at 130,000 miles per hour, relative to our solar system, not unusual by itself for an interstellar visitor. What was unusual was the path. Remarkably straight, remarkably flat. Not the chaotic curved trajectory you'd expect from an object that's been gravitationally perturbed by stars and planetary systems for billions of years. When you trace that trajectory backward through time, when you run the calculations to estimate where this object came from, the path points toward the outer regions of the early Milky Way, a region of space so distant that light from there takes tens of thousands of years to reach us. That's where 3i Atlas began its journey, somewhere in the galactic frontier, in conditions utterly unlike anything in our solar system. And the age estimates, these are speculative but grounded in plausible physics, suggest this object could be 7 to 12 billion years old. 12 billion years! That would make it 3 billion years older than our Sun. It existed when the universe was less than 2 billion years old, when galaxies were still colliding and merging with wild abandon, when the Milky Way looked nothing like the spiral structure we see today. This object has witnessed cosmic history on scales we struggle to even conceptualize. And somehow, through all of that, through billions of years of exposure to cosmic radiation, through passage near countless stars and their gravitational wells, through regions of space thick with interstellar gas and dust, 3i Atlas remained intact. It didn't fragment into a debris field. It didn't sublimate away entirely during previous close encounters with other stars. It survived. That survival itself is remarkable. Statistically improbable. Objects travelling through interstellar space face constant bombardment. Micrometeorite impacts at relative velocities that turn tiny dust grains into kinetic weapons. Cosmic rays that gradually break down molecular bonds and transform chemical compositions. Gravitational stresses during close approaches to massive objects. Any one of these processes could destroy or fundamentally alter a comet-sized object over billions of years. Yet 3i Atlas made it to our solar system still massive enough, estimated at 33 billion tons, to create the spectacular display we witnessed at Perihelion. Something about its composition, its structure, or the specific path it took through the galaxy, allowed it to endure when countless other objects would have disintegrated long ago. So, as October 29th arrived and 3i Atlas reached that critical perihelion point, multiple instruments were watching as carefully as geometry would allow. And what they documented wasn't just interesting, it was paradigm-challenging, because the official explanations being crafted, the natural mechanisms being proposed to account for the explosive brightening, they work on paper, they're plausible, carbon dioxide sublimation creating protective insulation that suddenly fails, exposing water ice to direct radiation, and triggering runaway vaporization that's good physics. It fits observation. But as more data has been analysed, as researchers have dug deeper into the measurements from those critical hours, subtle inconsistencies have emerged. Details that don't quite match predictions, timing issues that complicate the simple narrative. And that's created an undercurrent of uncertainty in the astronomical community, a sense that maybe we're seeing something genuinely unprecedented, something that will require us to expand our models in ways we haven't fully appreciated yet. Before we dive deeper into what makes 3I Atlas so profoundly unusual, we need to understand something fundamental about what billions of years in interstellar space actually does to an object. This isn't abstract theory, this is documented physics we can model and test. Our solar system exists inside a protective bubble called the heliosphere, created by the constant stream of charged particles our sun emits. That bubble shields us from the full force of galactic cosmic rays, those high-energy particles born in supernova explosions and accelerated by magnetic fields to speeds approaching light itself. Within our heliosphere, we're relatively safe. The solar wind deflects most of these particles, but step outside that bubble, into the vast darkness between stars, and there is no protection whatsoever. An object drifting through interstellar space is exposed to relentless bombardment. Particle impacts that gradually, inexorably transform everything they touch. The James Webb Space Telescope observed 3I Atlas back in August 2025, months before Perihelion, using its near-infrared spectrograph to examine wavelengths invisible to human eyes. Webb revealed something researchers had suspected but needed confirmation on this comet, bears the unmistakable signature of cosmic ray damage. The outer layers have been chemically transformed by billions of years of radiation exposure. Carbon monoxide converting to carbon dioxide, crystalline ice structures breaking down into amorphous forms, organic molecules fragmenting and recombining in new configurations. The radiation doesn't just alter surface chemistry, it penetrates deep, creating what researchers call a radiation-processed crust. Computer models simulating this process suggest that after approximately 1 billion years, the transformation reaches roughly 50 to 65 meters into the object's interior. Beyond that depth, pristine material might still exist, still carrying the original chemical signature of whatever stellar system created this comet. But the outer shell has become something else entirely, a fusion of radiation-damaged products, hardened by eons of particle impacts into a protective armor that shields the interior from further damage. Think about what that means for understanding this object. We're not looking at a pristine sample from another star system. We're looking at something that's been fundamentally transformed by its journey. The outer layers tell us more about the billions of years of travel than they do about the origin. It's like trying to understand ancient pottery by examining only the layers of patina and corrosion rather than the original clay beneath. You can learn something valuable about the object's history from that damage, but you can't reconstruct its original form. That radiation crust is simultaneously evidence of the object's extraordinary age and an obstacle to understanding its true composition. Unless solar heating at perihelion stripped away enough of that crust to expose deeper layers, which is precisely what some researchers are hoping happened, we may never know what 3I Atlas looked like when it first formed. But here's where this gets interesting from an engineering perspective, and yes, I'm going to address the question that's probably forming in your mind right now. If you were designing an object meant to survive billions of years of interstellar travel, if you were building a probe intended to carry instruments or information across galactic distances, would a radiation-processed crust be advantageous? Absolutely. It provides natural protection from continued radiation damage. It offers structural integrity that prevents fragmentation. It creates a thermal barrier that helps regulate internal temperatures. Every characteristic we've observed in that radiation crust aligns with what you'd want in a long-duration interstellar vessel. Now, before anyone jumps to conclusions, I'm not claiming 3I Atlas is artificial. The overwhelming likelihood is that this is a natural object with natural composition. But what I am saying is that the characteristics we observe, the protective crust, the extraordinary age, the unusual brightening pattern at perihelion, these characteristics happen to be consistent with both natural formation and deliberate design. That doesn't prove anything. It just means we should be thorough in our analysis and honest about what the data can and cannot tell us. The research on radiation damage also reveals something crucial for interpreting the perihelion observations. An object with a thick radiation crust would behave very differently from typical comets as it approaches solar heat. That crust acts as insulation, preventing water ice underneath from sublimating until the crust itself is compromised or breached. Then suddenly, explosively, the exposed ice faces direct solar radiation and begins vaporizing at catastrophic rates. That creates a threshold effect relative stability followed by rapid, dramatic change, which is exactly what we observed. For weeks, as 3I Atlas approached the Sun, its brightening was measurable but not extraordinary. Carbon dioxide was sublimating from the outer layers, creating that protective cooling effect researchers have documented. But then, right around perihelion, something changed. The carbon dioxide depleted, the protective barrier failed, and the water ice underneath ice that had been shielded from direct radiation for billions of years suddenly faced 33 gigawatts of solar energy. The result was that explosive brightening, that surge in sublimation rates, that blue shift indicating violent molecular emission. It's a plausible natural explanation, it fits the physics, and it's probably correct. But it also opens questions. If this radiation crust mechanism explains 3I Atlas's behavior, then other interstellar objects should show similar patterns. We should see more threshold brightening events, more explosive sublimation as protective crusts fail, more dramatic changes in activity level tied to specific solar distances where critical barriers are breached, and we can test that. As we encounter additional interstellar visitors in the coming years and decades, and we will, now that we know where to look and how to detect them, we'll accumulate data on whether this pattern repeats. If it does, excellent, the radiation crust model is validated. If it doesn't, if 3I Atlas remains unique, then we need to explain why this particular object behaves so differently from others with similar histories. Either outcome teaches us something valuable. Either way, we learn. That's how science progresses, through careful observation, through hypothesis testing, through honest acknowledgement when data doesn't match expectations. The cosmic ray research also connects to something broader that researcher Susanne Falsner from Forschungszentrum Jülich in Germany has been investigating. She's proposed that interstellar objects like 3I Atlas aren't just cosmic debris wandering aimlessly through the galaxy. They might be the seeds of planetary systems. Her model suggests that when massive stars with planet-forming disks pass through regions rich in these interstellar wanderers, they can capture millions of them gravitationally. These objects then become embedded in the protoplanetary disk, serving as nuclei around which additional material can accumulate. Over millions of years, some of these captured interstellar objects could grow into full planets. If that's true, then 3I Atlas isn't just an interesting comet. It's an example of planetary system building blocks, evidence of how materials and chemistry get distributed across the galaxy, how stellar systems exchange matter and potentially organic compounds over billions of years. That context changes everything about how we should study this object. We're not just characterizing one unusual visitor. We're examining a fundamental mechanism of galactic evolution, a process that might help explain why planetary systems show the chemical diversity we observe. Now we need to talk about something that's been brewing beneath the surface of the official scientific coverage. On October 30th, 2025, one day after perihelion, Avi Loeb made a formal request. Loeb is the former chair of Harvard University's astronomy department, director of the Galileo project, and someone who's built a reputation controversial in some circles, respected in others for pushing boundaries on how seriously we should take unusual astronomical observations. He asked NASA to release all scientific data on 3I Atlas to the public, not summaries, not press releases, not carefully curated findings published through traditional peer review channels. Everything, every spectrum from every instrument, every image from every angle, every measurement collected during that critical perihelion window. His argument was straightforward. This is an object of extraordinary scientific importance, only the third confirmed interstellar visitor in human history, and the data represents our best chance to understand these phenomena. That data, he argued, should be available for independent analysis by researchers worldwide, not controlled by any single institution or research group. On the surface, this seems reasonable. Science benefits from transparency. Multiple research teams examining the same data from different perspectives often catch patterns and anomalies that single groups miss. Cross-disciplinary analysis brings fresh approaches that specialists sometimes overlook. Open data has become standard practice in many areas of astronomy, precisely because it accelerates discovery and reduces the risk of confirmation bias. But Loeb's request carries an implicit question underneath, one that resonates with anyone who's followed the Oumuamua controversy from 2017. What exactly is in that data? What has been observed that hasn't been publicly discussed? Are there measurements, spectra, or behavioral patterns that don't fit easily into neat press releases and preliminary papers? Are there complications to the official narrative that are being downplayed or set aside pending further analysis? Now, I need to be very careful here about how this gets framed. The mainstream astronomical community has offered detailed explanations for 3I Atlas's behaviour. Zhang, Battams, and numerous other researchers have documented their observations, published their methodologies, and subjected their findings to peer scrutiny. Their work is rigorous. Their explanations are grounded in established physics. The carbon dioxide sublimation model, the radiation crust hypothesis, the threshold brightening mechanism, these are all testable, falsifiable scientific proposals supported by observation. There is no evidence of a cover-up. There is no reason to believe data is being deliberately suppressed or misrepresented. But that doesn't mean Loeb's request is unreasonable. In fact, it reflects something important about how modern science should operate. When we have unprecedented observations of rare phenomena, transparency serves truth better than gatekeeping. Releasing comprehensive data allows the global research community to validate findings, propose alternative interpretations, and potentially discover patterns that initial analysis teams didn't notice. The challenge is that modern astronomical instruments produce staggering amounts of raw data, terabytes upon terabytes of measurements that require extensive processing, calibration, and validation before they become scientifically useful. You can't just dump raw instrument telemetry online and expect independent researchers to make sense of it without the calibration files, the processing pipelines, the detailed documentation of instrument characteristics and known artifacts. That groundwork takes time. It requires careful work by teams who understand the instruments intimately. And there's also the legitimate academic incentive structure to consider researchers who design observations, who fight for telescope time, who invest months or years in planning missions, reasonably expect priority access to analyze their data first. That's how the system has traditionally worked, and it's produced remarkable science. But that system can also create problems if data is held too long, if certain interpretations dominate before alternative analyses have opportunities to emerge, if institutional pressures discourage exploration of unconventional hypotheses. The healthy resolution, the one that serves scientific progress best, is transparency with reasonable timelines. Publish data processing pipelines and calibration protocols immediately so other researchers can prepare. Release preliminary findings rapidly, even before formal peer review, through preprint servers like ARXIV. Engage the broader community in real-time analysis rather than waiting months for traditional publication. And this is actually happening more frequently in modern astronomy. The Zhang and Battams preprint was published on ARXIV before Perihelion even occurred, making their methodology and initial findings available while events were still unfolding. That's excellent practice. That's how collaborative science should work. But the question remains, is all the data being shared? Are there observations from instruments we haven't heard about yet? Are there measurements that showed anomalous or unexpected results that are still being analysed behind closed doors? I can't answer that definitively because I don't have access to classified data, if any exists. But the question itself is worth asking because it reflects proper scientific skepticism, not cynicism, not conspiracy thinking. Just a healthy insistence that unusual observations deserve comprehensive investigation rather than premature closure around convenient explanations. If there are additional observations, spectroscopic details that complicate simple models, timing anomalies that don't quite fit carbon dioxide sublimation curves, structural features in perihelion images that suggest unexpected internal composition, those should be documented and discussed, not sensationalized, not used to jumping to wild conclusions, but honestly examined as part of the full picture of what 3I Atlas revealed during those critical hours. And this connects back to transparency serving science better than secrecy. When data is openly available, when methodologies are clearly documented, when alternative interpretations are welcomed rather than dismissed, the research community collectively becomes more capable of distinguishing signal from noise, genuine anomalies from instrumental artifacts, revolutionary discoveries from prosaic explanations. We get smarter together, we catch errors faster, we refine models more effectively. That's the argument for Loeb's request, stripped of any suggestion of conspiracy or hidden agendas, just straightforward insistence that unprecedented observations of rare phenomena deserve the most thorough, collaborative, transparent analysis possible. Now let's talk about what the trajectory reveals, because sometimes the most important information about an object isn't what it's doing, it's where it came from and where it's going. The path of 3i Atlas through our solar system is remarkable in its straightness, its flatness, its directionality. This isn't the chaotic curved trajectory you'd expect from an object born in our solar system, perturbed by planetary gravity wells, scattered by close encounters with gas giants. This is a path that announces clearly, I came from somewhere else, and I'm just passing through. The velocity tells part of that story 130,000 miles per hour relative to our solar system, fast enough that gravitational capture is impossible. Once 3i Atlas completes its swing past the Sun, it will head back out into interstellar space, and we will never see it again. This is a one-time event, one precious observation window, as an ancient wanderer crosses our cosmic neighbourhood and vanishes. That makes every measurement during this passage irreplaceable. Every spectrum matters. Every image contributes to what will ultimately be our only chance to study this specific object. The age estimates, while speculative, are staggering. 7 to 12 billion years. If those numbers hold up under scrutiny, this object existed before our Sun ignited, before Earth formed from the protoplanetary disk, before any planet we know came into being. It has drifted through the galaxy since an epoch when the Milky Way looked fundamentally different from today, when different stars dominated different regions, when galactic structure was still settling from ancient collisions and mergers. What has this object witnessed? What stellar environments has it passed through? What supernovae exploded in its vicinity, bathing it in exotic particles and radiation? What molecular clouds did it traverse, potentially collecting materials from regions enriched by previous generations of stars? We'll never have complete answers to these questions. All we have is this moment, this passage through our detection range and the data we manage to collect before it fades from view. The trajectory calculations also reveal approximate origin, not a specific star, but a general region of the early galaxy. The outer frontiers, places where stellar density was lower, where the environment differed significantly from the inner galactic regions where our Sun eventually formed. That origin tells us 3i Atlas carries chemical signatures from a different stellar neighbourhood, different enrichment history, different planetary formation conditions, and that makes it valuable beyond its individual characteristics. It's a sample from a stellar environment we can never directly visit, carrying information encoded in its composition that we can extract through careful spectroscopic analysis. Each interstellar object that passes through our solar system is essentially a messenger from distant stellar systems, delivering information we cannot obtain any other way. The question is whether we're sophisticated enough in our analysis to read that message accurately. The survival of 3i Atlas through billions of years of interstellar travel is itself remarkable. Statistically, objects travelling through open space should experience higher collision rates with interstellar dust and gas. They should encounter gravitational perturbations from passing stars that could fragment them or strip away outer layers. They should suffer radiation damage that weakens structural integrity until they crumble into debris fields. Yet here it is intact, coherent, massive enough to create dramatic sublimation displays when heated by our Sun. That survival suggests either remarkable luck in the specific path it took through the galaxy, avoiding the densest regions and most disruptive encounters, or it suggests composition and structure unusually resistant to the forces that destroy most objects over these timescales. Either way, we're looking at an outlier, something exceptional that managed to endure where countless others would have failed. And the velocity itself carries information. Objects don't randomly achieve these speeds. They're accelerated by specific mechanisms, gravitational slingshots around massive objects, ejection from stellar systems during planetary formation, possibly even propulsion by radiation pressure if they have the right structural characteristics. The specific energy state of 3i Atlas, its momentum relative to the galactic reference frame, all encode information about its history that researchers are working to extract. Where did the energy come from? What events shaped this trajectory? Can we trace the path backward with enough precision to identify candidate origin stars? These are active research questions that the trajectory data helps address. What matters for our understanding now is that 3I Atlas arrived here on a very specific trajectory at a very specific time, and that timing allowed us to observe it during perihelion with instruments we've developed over decades, specifically for studying solar phenomena. If it had arrived a century earlier, we would have missed it entirely. If it arrives a century from now, we'll have different instruments, different capabilities, perhaps better understanding of what to look for. But this is our moment, the time when this ancient object and our observational technology align to give us this chance. And in the coming weeks, as it continues moving away from the Sun through November and December, we're racing against time to collect as much additional data as possible before it fades beyond efficient observation range. By late December, it should drop below magnitude 12, becoming too faint for amateur equipment. By January 2026, it will be essentially gone from easy reach. The window is closing, and everything we want to learn about this object, its true composition beneath that radiation crust, its internal structure, its origin, its nature, we need to extract before that window closes forever. When light from 3I Atlas reached our instruments during perihelion, it didn't just carry brightness information. It carried a story written in wavelengths, encoded in the specific frequencies of photons that had interacted with molecules escaping from the comet's nucleus. Spectroscopy is how we read that story, breaking light into its component wavelengths and analysing which frequencies are present, which are absorbed, which are enhanced. And the story 3I Atlas told was complex and surprising. That blue shift we discussed earlier, the spectral shift toward shorter wavelengths, revealed specific molecular emission. Carbon molecules, specifically C2, dominate the visible spectrum. Nitrogen-hydrogen compounds, NH2, appearing in infrared wavelengths. These are the chemical fingerprints of violent sublimation, of ice transforming directly to gas at extraordinary rates. But the dominance of gas emission over dust reflectivity was unexpected. Most comets at that solar distance show significant dust in their coma, particles reflecting sunlight and creating that characteristic brightness. 3I Atlas showed primarily molecular emission, actual gas molecules radiating photons as they transitioned between energy states. That tells us either this comet is unusually Icaric with minimal dust-forming materials, or the dust is being suppressed somehow, perhaps trapped beneath that radiation crust and not effectively escaping, even as gas vaporizes. The water production rates measured during the perihelion passage, 1.36 times 10 to the 27th power molecules per second, represented such extreme sublimation that researchers had to carefully verify their measurements. These aren't numbers you see in typical cometary observations. Even very active comets rarely approach these production rates. The sheer volume of water escaping suggested something fundamental about internal structure, either enormous exposed surface area of ice in contact with solar radiation, or some mechanism concentrating heat and vaporization beyond simple solar heating. Traditional comet models predict gradual increase in water loss as solar distance decreases, following smooth curves determined by temperature changes. But 3I Atlas showed almost explosive acceleration in production rate right around perihelion, that threshold behavior consistent with sudden barrier failure rather than gradual heating. The James Webb Space Telescope's observations from August, months before perihelion, had confirmed high carbon dioxide concentrations through near-infrared spectroscopy. Webb can resolve molecular absorption lines with extraordinary precision, distinguishing between different carbon compounds, different ice phases, different chemical environments. The carbon dioxide Webb detected was sublimating even when the comet was still far from the Sun, 3 times Earth's orbital distance. That's unusual. Most comets don't lose significant carbon dioxide until much closer solar approaches. But if you're building a model where carbon dioxide creates protective cooling, or its sublimation prevents water underneath from vaporizing, then detecting strong carbon dioxide at large distances makes perfect sense. It's exactly what you'd expect if this mechanism explains the perihelion behavior. The explanation researchers are converging on goes like this. As 3I Atlas approached the Sun, increasing solar radiation began sublimating carbon dioxide from outer layers of that radiation-processed crust. The phase changed from solid to gas-absorbed energy, creating a cooling effect that actually lowered temperature at the ice-gas interface despite increasing solar flux. This protective mechanism kept deeper water ice from reaching sublimation temperature, but as solar distance continued decreasing, More and more carbon dioxide was lost, gradually depleting that protective layer. Then, at some critical threshold right around perihelion, the carbon dioxide concentration dropped below the level needed to maintain cooling. Suddenly, water ice faced direct solar radiation without that buffering effect. The temperature spiked above water's sublimation point. An explosive vaporization began, stripping away surface layers and exposing fresh ice underneath, which immediately began sublimating as well, creating that runaway brightening we observed. It's elegant physics. It fits observation. It explains the timing, the threshold behavior, the production rates, and it's probably correct. But, and this is important, this explanation assumes that all the unusual features can be attributed to this specific mechanism. It assumes carbon dioxide concentration is the primary variable controlling behavior. It assumes internal composition is relatively homogeneous beneath that outer crust. It assumes no other processes are contributing significantly to the energy budget or the sublimation dynamics. Those are reasonable assumptions, but they are assumptions. And if post-perihelion observations reveal behavior that deviates from what this model predicts, then we have evidence that those assumptions need refinement. That's why the observations happening right now in November 2025 are so crucial. As 3I Atlas moves away from the Sun, as solar heating decreases, the model predicts specific things should happen. Water production rates should decline following the inverse of the heating curve. The spectroscopic signatures should shift as gas emission decreases. The brightness should fade in predictable ways, matching decreasing sublimation. If all those predictions hold, excellent. The carbon dioxide cooling model is validated. But if observations show anomalies, if water loss remains elevated despite decreasing solar flux, if new spectroscopic features emerge, if brightness doesn't fade as expected, then we have evidence for complications. Maybe internal heat sources contributing to continued sublimation. Maybe structural asymmetries creating differential heating. Maybe compositional variations exposing different materials as surface layers erode. Any of those would be fascinating scientifically, and would require expanded models incorporating factors we hadn't previously considered. The spectroscopy also carries information about 3I Atlas's origin environment. Different stellar systems have different chemical abundances. Elements are distributed unevenly across the galaxy, enriched in some regions by nearby supernovae, depleted in others by stellar winds carrying materials away. Water, carbon dioxide, nitrogen compounds. Their relative concentrations vary depending on where and when an object formed. So if researchers can precisely characterize 3I Atlas's spectroscopic signature, comparing it against known stellar populations and their expected chemistry, they can potentially constrain what type of stellar neighborhood birthed this comet. Maybe not the specific star, but the class of environment. That tells us something about galactic chemical evolution, about how materials get distributed, about the diversity of planetary formation conditions across our galaxy. For that hypothesis about interstellar objects seeding planets, Suzanne Falsner's model spectroscopy becomes particularly important. If these objects carry distinct chemical signatures from their origin systems, and if they get captured by new stellar systems during planetary formation, then they're literally transporting chemistry between stellar neighborhoods. They're enriching planet-forming disks with materials from completely different galactic environments. That could fundamentally affect what kinds of planets form, what organic chemistry is available, even potentially what conditions exist for life to emerge. It's a galaxy-wide process of chemical exchange operating over billions of years, with objects like 3I Atlas as the carriers. That elevates what we're studying from interesting individual comet to fundamental mechanism of galactic evolution. Right now, in early November 2025, we're in the most critical observation window for 3I Atlas since perihelion. The comet has moved far enough from the Sun that ground-based telescopes can observe it directly without solar glare interference. For the next 4 to 6 weeks, before it fades below magnitude 12 and becomes difficult for amateur equipment, before it drops below magnitude 15 and becomes inefficient even for professional observatories, we have this precious window. Researchers worldwide are collecting data every clear night. Spectroscopy tracking how emission lines evolve. Photometry measuring precise brightness changes. Imaging documenting structural changes in the coma. And everyone is asking the same question. Will 3I Atlas continue surprising us, or will it settle into predictable behavior that confirms natural explanations? The specific questions astronomers are testing right now are precise and quantifiable. Is the brightness decreasing at the rate predicted by standard comet models? Is water production declining proportionally with decreasing solar flux? Are spectroscopic signatures shifting toward lower excitation states as expected when temperatures drop? Any deviation from predictions tells us something important. It means our models need refinement. It means additional factors are influencing behavior beyond what we initially considered. And those deviations, if they exist, might only be detectable during this narrow window before the comet becomes too faint for detailed analysis. There's also data we're still waiting on. The Mars rovers, Curiosity and Perseverance had unique vantage points during perihelion at different angles, different geometries than Earth-based or space-based solar observatories. Their cameras aren't optimized for comet observation, but they captured images. Those images are being processed, analyzed, compared against other observations. What did they show? Did they reveal structural details invisible from Earth perspective? Did they catch asymmetries in the coma, variations in brightness across the nucleus, anything that might indicate internal dynamics or compositional heterogeneity? We'll likely see papers on this in coming months, as that data becomes publicly available. The solar-wind interaction data is another area of active analysis. When 3I Atlas passed close to the Sun, it ploughed through the solar wind, that continuous stream of charged particles flowing outward from our star. That creates observable effects, magnetic field distortions, plasma instabilities, particle acceleration around the comet's coma. Stereo and other solar missions captured those interactions. The patterns revealed in those observations tell us about the comet's magnetic properties, its plasma environment, how its outgassing interacts with external forces. Understanding those patterns requires sophisticated plasma physics and magnetohydrodynamics modeling, work that takes months to complete properly. But when finished, it will reveal aspects of internal structure and composition that spectroscopy alone cannot determine. The solar wind essentially probed the comet in real time, and we're now working to interpret what that probe revealed. As November progresses toward December, 3I Atlas will continue its journey outward, travelling through the constellations Virgo and Leo, fading gradually from view. The brightness will drop steadily at first, then more rapidly as sublimation decreases exponentially with temperature. By late December, most amateur observers will have lost it. By January, even professional telescopes will find it inefficient to observe too faint to gather useful data quickly, better to allocate telescope time to brighter, more accessible targets. When that happens, when observation becomes impractical, we will have learned what we could learn from this visitor, and we'll spend years analysing and debating what it all means. Different research groups will propose competing interpretations of the data. Some will argue that natural explanations, carbon dioxide sublimation, radiation crust failure, standard compositional variations fully account for observations. Others will propose complications, additional mechanisms, refined models incorporating factors that initial analyses overlooked. And maybe, years from now, some researcher will notice a subtle pattern in the spectroscopy, or a timing correlation that everyone else missed, and everything will shift. New understanding will emerge. That's how science progresses slowly, through careful accumulation of evidence, through honest debate about interpretation, through willingness to refine models when data demands it. The implications of what we learn from 3I Atlas extend far beyond this one object. If billions of these ancient wanderers are drifting through the galaxy, all carrying chemical signatures from distant stellar systems, all potentially seeding planets when captured by young stars, then the galaxy is fundamentally more interconnected than we've historically understood. Chemistry and materials are constantly moving between stellar neighborhoods. Planetary systems aren't isolated islands. They're nodes in a galactic network of chemical exchange operating over billions of years. That changes how we should think about planetary formation, about chemical evolution, about the distribution of organic materials and potentially even life-enabling chemistry across cosmic scales. And if we can master studying these objects, if we can extract maximum information from their brief transits through our detection range, then we're developing a tool for understanding stellar systems we can never visit. Each interstellar object is a physical sample from a distant environment, carrying information encoded in its composition and structure. The question is whether we're sophisticated enough in our analysis to decode that information accurately. 3I Atlas is teaching us how to do that. Every measurement, every spectrum, every observation is refining our ability to study the next interstellar visitor. And there will be others, Sooner or later, another object from the deep galaxy will pass through our solar system. It will be different. It will teach us different lessons, and hopefully we'll be wiser about studying it because of what we learned here. This is the story of Three-Eye Atlas, an ancient wanderer from the galactic frontier, carrying secrets of the deep past, passing through our cosmic neighborhood and revealing mysteries we didn't know existed. The observations are still happening. Amateur astronomers with capable telescopes can still see this comet if they know where to look. Professional observatories are still collecting data every clear night. The story hasn't finished. And when you follow along as new findings emerge over the coming weeks, you're participating in real-time science. You're witnessing how discovery actually works through careful observation, through honest debate, through collective investigation by researchers worldwide collaborating to understand something genuinely unprecedented. The interstellar visitor delivered its message through that explosive brightening at Perihelion. Now we're working to understand what that message means. And whatever we learn, whether it confirms our models or forces us to expand them, we'll know more about the universe than we did before this ancient traveller crossed our sky.